Welcome to Cup of Physics, a channel which makes a topic which totally isn't your cup of physics into a topic which at least kind of is your cup of physics. Today we're starting with a past paper from A-level. This is a past paper from February-March 2016, variant 22. And we can start with question 1. The speed v of a transverse wave on a uniform string is given by the expression v equals to root of TL over m, where T is the tension in the string, L is the length, and m is its mass. An experiment is performed to determine the speed v of the wave. The measurements are shown in figure 1.1. State an appropriate instrument to measure the length L. Now you have to ask yourself which one will give the most precise and accurate results. The answer to this would be a measuring tape. It's going to be longer than 1 meter rule, and we definitely want to avoid making two measurements. Because if we choose a meter rule and make two measurements, it means that the associated error with this is going to be higher, which means the uncertainty is going to be bigger as well. And we want to avoid that. We want to keep our results as accurate as possible. Part B. Use the data in figure 1.1 to calculate the speed v. Now, the equation is already above, so don't use any other equations for speed v. You were already given the thing that you are meant to work with. Popping everything into the equation, just remember to convert all of the measurements from derived units into base units. This means length will need to be converted into meters from centimeters, and grams will have to be converted into kilograms, which gives you the answer of 444.7 meters per second. Don't forget to include the units, and remember that the amount of significant figures that I wrote down here is too many. So I want to cut these down to an A-level standard, which is usually 3 significant figures. If you want an explanation with regards to why you should be using 3 significant figures, feel free to click here. Top right, that is. In the next part, you should use your answer and the data in figure 1.1 to determine the value of v with its absolute uncertainty to an appropriate number of significant figures. You should know that this is a classical finding the uncertainty answer. You're going to look at uncertainties in year 12 and then you usually continue with them in year 13 if you continue with physics, that is. Because paper 5 is definitely going to involve calculations of uncertainties, so it's wise for you to know this stuff now. Start by rewriting the equation in standard form. This is going to make the process easier for you. Then you can ask yourself, which type of formula is this? Well, we can see that this is multiplication. You really only have 2 options to go with, but you should be able to turn any formula into either multiplication formula or addition/subtraction formula. In this case, it is multiplication, so you know that you should be using fractional uncertainty. Oh, and by the way, if you want to remind yourself why you should be using fractional uncertainties, feel free to click here. Anyway, since the video about uncertainties will probably not be published super soon, I've decided to explain a little bit more about uncertainties here. So remember that the absolute uncertainty is just delta t, for example. In my case, delta v or dv. The fractional uncertainty is then dv over v, and the percentage uncertainty is dv over v times 100%. Now, what we have in the equation here are all fractional uncertainties. If we look in the table above, we can get the values for all of them and calculate them. If we now plug them into the equation that we have here, we can calculate dv over v, which is 0.04. But wait, the question wants us to get absolute uncertainty, whereas we still have fractional uncertainty. So what we need to do now is multiply 0.04 times v, which is the value that we calculated before, 445, to get our dv, so the change in v, or the absolute uncertainty in v. This gives you a value of 17.78 meters per second. But remember that you also have to give your values to an appropriate number of significant figures. We know by now that this is 3 significant figures for the value of v, and the value of delta v has to be given to the same amount of decimal places. Hopefully, this makes a topic which totally wasn't your cup of physics into a topic which at least kind of is your cup of physics. If you have any questions or comments, please leave them below. Thanks for watching!